So I want to talk to you today about a part of my research which is related to morphing attack detection. And in this particular research, I want to discuss a method to improve deep learning-based face recognition in such a way that it is more robust against morphing attacks. So I'm a member of the Data Management and Biometrics group at the University of Twente in the Netherlands. And this is my PhD topic. All right, so I want to start today by talking a little bit about face recognition and specifically a convolutional neural network that I trained called VGG Face. Then I want to talk a little bit about what happens to these kinds of face recognition networks when you look at morphs and what morphs are. And then next I will describe a little bit why face recognition systems are vulnerable to morphs. And then finally I will discuss a little bit how you can improve this vulnerability. All right, so what does face recognition do? If you have a face recognition system, you give it two photos and you ask us, is this the same person? Yes or no? So a good one in this particular scenario would say, no, this is not the same person. So I worked with a specific convolutional neural network called VGG Face that consists of 16 layers, and it has as an input, it has an image of a face, and it outputs an embedding in a 64-dimensional space. You train it with triplets like these. I will describe in a moment what these kind of triplets, what they mean. So a triplet consists of the embeddings of three different photos. So I have two photos of the same person. The first one I call the anchor. The second photo of that same person I call the positive example. These X's are the embeddings of the photos as calculated by the neural network. And then I add a third photo of a different person. So again, the first two photos are of the same person, and then I add a third photo of a different person, so someone with a different identity. And again, this X negative in this example is then the embedding determined by the convolutional neural network for this third photo. So I trained this particular neural network with this loss function, which you can see a little bit. To intuitively understand what this loss function means, it means that you look at the distance between the anchor and the negative, so the two photos of two different people, and you take the distance squared, and you look at the difference between the distance squared of the anchor and the negative, and the distance squared of the anchor and the positive. And you want the difference between these two values to be at least alpha. If this criterion is fulfilled, then the maximum of the 0 and this particular value is then 0, so your loss function becomes 0. So this would be a scenario for a particular value where your loss function is not equal to 0 because the distance from your anchor to your positives squared is larger than the distance from your anchor to your negative squared. By the way, here, so I mentioned before that these embeddings lie in a 64-dimensional space. You can't visualize that. So I simplify the idea a little bit by showing these in a 2-dimensional space. So I will describe shortly what kind of data I use to train this network. So it consists of triplets, as I mentioned. So each column in this particular picture describes one triplet. So you have the first photo of a person, a second photo of the same person, and a third random photo of a completely different person. So these are 4 examples of these kind of triplets. In my data set, I have photos of 514 different people, and I have about 20,000 photos of these people. And I save a couple of photos for testing later to evaluate my results. So next, I would like to describe a little bit how you make these triplets. So you start, the first step is to make a list of all possible genuine pairs. In biometrics, we call these genuine pairs because these are 2 photos of the same person. So I go through my 20,000 photos and I look at all possible pairs of the same people that I can make. And then while I train, to each of these pairs, I add a negative example such that the anchor and the negative together form an imposter pair. So that's what we call in biometrics. When you have a pair of 2 photos of 2 different people, we call it an imposter pair. So now I have a set of triplets. And during training, I keep the genuine pairs constant, but the third sample, the negative sample that I always pick, is chosen random, so it's different. It changes during training. So again, so a triplet looks like this. You have an anchor and a positive and a negative example. So this would be an example. This is a nice example because the distance between, so what you want in the end, you want your network to have a good face recognition system. You would like it to output a small distance for photos of the same people, but a large distance for photos of different people. So you can describe this with something that we call a triplet criterion. Namely, that we want the distance of the anchor to the negative squared, and the difference of that with the anchor and the positive squared to be smaller than alpha. So the example I showed here this criterion is fulfilled because this distance is smaller than this distance with a certain buffer of alpha. This is an example where it doesn't hold because the distance between your anchor and your positive is the same as the distance between your anchor and your negative. We call these hard triplets because the network is not able to classify these properly. And here's a third example that is even worse because the distance between your anchor and your positive is actually larger than the distance between your anchor and your negative. Okay, so back to the pictures. A good face recognition system, if it was trained this way, and I will show in a moment that this works in most cases, when it compares a photo of one person with a photo of a second person, it says, yes, this is the same person. And the same when I compare a photo of this person with a photo of the same person, it will say, yes, this is the same person. And on the other hand, when it compares this photo with this photo, or maybe this photo with this photo, it should output, no, this is not the same person, and the same in this scenario. Now, when I do this many, many times, I can look at the distances that are outputted. So here, the blue histogram describes the genuine distances. So for all possible genuine pairs that I can make, I can calculate the distance between the embeddings. And you see that these distances tend to lie between 0 and roughly 0.7. Whenever I take pairs of photos of different people, so imposter pairs, then the distances are a lot larger. So you can put a threshold somewhere, a decision threshold, and then say if a distance is below this particular threshold, then I will make the decision and say, no, this is not the same person. If the distance between the embeddings is above the threshold, I will say, sorry, I said it the wrong way around. So if it's below the threshold, it is the same person. If the distance is above the threshold, it is not the same person. So there are two types of mistakes you can make here. You can either falsely accept a match of two photos of two different people. So they should have been rejected, but instead they were accepted. So we call that a false match rate. So it's the proportion of the imposter comparisons, so photos of two different people, that were accepted, divided by all possible comparisons that you could make. And the other type of mistake you can make is the false non-match rate, which is any genuine comparisons, so two photos of the same person that were rejected, even though they shouldn't have been. And the proportion of these rejected comparisons versus all possible genuine comparisons. So these are the two types of errors you can make. So you can find, for example, if I were to put the threshold over here, then I could try to find a spot where those errors are equal. The threshold that is usually used in practice at airports, for example, as automatic face recognition systems used at airports, is they look at where the false match rate is equal to 0.1%. So at most 1 in 1,000 imposter comparisons is accepted. And you can look at where can I put the threshold so that the false match rate is 0.1%. And then I can look what is the false non-match rate at this particular threshold. So during training, I trained for 200 epochs, this particular network with the data that I mentioned before. And you see that as you train, this value becomes lower and lower, which simply describes that the distributions, the two different distributions, are separated better and better during training. And we end up at the end with a false non-match rate of about a bit more than 2%. Now, what happens with morphs? So first, what are morphs? Let's say I take 2 photos of 2 different people. What I can do is I can look at landmarks, interesting marks in the face of one person. Then I can divide up the picture of this person using these landmarks into triangles. I can do this for both photos. So I pick corresponding landmarks in this other face, and I do the same thing there. I divide the face into triangles. Now what I can do next is I can use the landmarks to figure out what the sort of average geometry of the face is. And I can also use the triangles because I have for each triangle in the left photo, I have exactly the same triangle corresponding in the second photo. So I can look for each pixel in this image. I can figure out which pixel it corresponds to in this image. So I can look at the landmarks to find an average geometry, and I can use this pixel information to find the average pixel values. So I do that to create something that we call a morph. So this is a new photo that I created that looks a little bit like it's in between these 2 photos. Here you see something that we call ghosting artifacts. It's because I also morphed the background of these 2 images. So to remove these ghosting artifacts, what you can do is you can cut out the inside of this face, of this morph, and I can paste it into the background of one of the original photos. Here, I took the inside of this face and I pasted it into this second background over here. We call this step splicing. And since a good face recognition system doesn't focus too much on hairstyle, for example, or clothes that a person is wearing, since you can dye your hair or you can change your hairstyle, so an automatic face recognition system shouldn't focus on that too much. It doesn't matter, so the difference between these 2 photos for a face recognition system is not too large. And it turns out, indeed, when I compare this morph with this photo, it is accepted. In many, many cases, it will be accepted by the face recognition system. On the other hand, also this pair will be accepted as a match. So this opens up kind of opportunities for fraud, because someone who is a criminal and is not allowed to travel or is not allowed to enter a particular country could ask an accomplice to go apply for a passport with a morphed photo that they created. This accomplice doesn't have a criminal record, is allowed to enter specific countries, and applies for a perfectly valid passport using this morphed photo, because he looks sufficiently like the photo to be able to be accepted at a passport application office. The second person can then use this passport and travel, even though they are not allowed to travel or on some kind of a blacklist or not allowed to enter a country. So it opens up options for fraud. When you look at a face recognition system, we described earlier, I described the genuine comparisons that you can look at and the imposter comparisons. These types of comparisons where I compare a morph with one of the people who contributed to making this morph, I call these morph comparisons. And I made a histogram again of morph comparisons. And you suddenly see that if I were to put a threshold, a decision threshold over here, right in between the genuine and the imposter distributions, I accept a significant number of morphed comparisons. So this is a problem. This has been shown in other research. This is an idea that was proposed by people from the University of Bologna in Italy. And it has been shown since then that many, many face recognition systems are vulnerable to this kind of morphing attack, what we call a morphing attack. And so are humans. So it's also been shown we as humans are good at recognizing people that we know very well. But for someone who works at border control and sees people they have never seen before in their life, this can be very challenging, and they face a similar problem that they will accept these kind of morph comparisons as a true match, even though they shouldn't. So what we need is, what we find out is that these 2 metrics that I introduced earlier, the false match rate and the false non-match rate, which is basically the false match rate is the proportion of the imposter comparisons that is below this threshold over here, this small triangle down here. And the false non-match rate is the proportion of genuine comparisons that is rejected. So this small triangle on this side. And these metrics don't describe the full problem when you look at morphs. So what we need as well is at a fixed threshold, we can look at the proportion of morph comparisons that are accepted. So that is a new metric to describe how well a face recognition system can work with, or how robust a face recognition system is to morphing attacks. So what you see when you train a face recognition network, this is the same plot I showed before, that during training, the false non-match rate at a fixed false match rate drops significantly, which is good because it means that the genuine distribution, the distribution of genuine scores or genuine distances is very separate from the distribution of imposter distances. But so like I mentioned, we need this new metric, which I call morphing accept rate. And you see that while during training, the separation of the two distribution is better and better, at the same time, the proportion of morphs that are accepted become higher and higher. So what I next thought was, is there a way that I can train a face recognition system that is good at separating genuine and imposter distributions, but at the same time does not accept more and more morphs as the face recognition system becomes better at separating normal photos? And my idea was to simply treat morphs as new identities and to include these in the training sets that consist of the triplets that I described before. So here's an example of the kind of triplet that you could have. You could have a triplet that consists of two photos of the same person. And then the third, the negative example, is a photo of a morph of this person with a different person. So as I mentioned before, the face recognition network is trained to minimize this distance and to maximize this distance. However, one thing that you come across is that face recognition systems that are based on deep learning need large amounts of data for training, which means that you also need large numbers of morphs. However, so that means you are forced to make some kind of an automatic pipeline to create morphs. What you come across then is that you find artifacts in your image. For example, here you find artifacts of one person who was smiling and another person who was not smiling. Here you find an artifact of one person who had a little bit of hair in front of their face and the other person didn't. And these are the kind of artifacts that you will come across when you try to create large morphing databases. A criminal, on the other hand, hypothetically, would probably have several days to create one very good, convincing morph. So they would make sure that these kind of artifacts were not present in the photo that we would use to apply for a passport at the passport application office. And what we don't want to happen is that the network is able to separate genuine pairs that consist of an anchor and a positive, and imposter pairs, anchor and negative, based on these artifacts. We would like it to learn that a face compared with a morph is not a true match because the identity information is not sufficiently similar. We don't want it to overfit on finding artifacts because we assume that in practical scenarios, these kind of artifacts wouldn't be present. So one way would be to clean up the data set of morphs. But since you need very large amounts, or very large numbers of photos, this is not realistic. So what we decided to do was to try introducing, instead of removing the artifacts in the morphing data set, was to artificially also include them in the normal data set, which we achieved by taking photos of a specific identity. For example, here, these are 3 photos of the same woman. And we create what we called augmented genuines. So these are, for example, this is a photo of this person, this photo morphs with this photo. So 2 times the same person. And I will consider this to be a new photo of the same identity. And the same over here. Again, this is also a morph of this photo with, I think in this particular case, it was this photo, or I'm not sure, it might be this one. But again, 2 times the same person and a morph. And you see that this has exactly those artifacts that we saw before. And the same here, a little bit of shade from hair that wasn't present in a different photo. So now we can have different types of triplets. What can happen is we can have a photo of identity number 1 and a second photo of identity number 1. And the negative sample can be a morph of the same identity with a different photo. The second column here describes a normal photo of some person, and then an augmented genuine of this same person, and then a third random different photo. What you could also have is a morph of person 1 and person 2, and then a second morph, again of person 1 of 2, but created using different photos of these identities. And then the third photo could be just a random different person. Or what could happen is you could have a triplet that consists of one morph of identity 1 and 2, a second morph of identity 1 and 2, created using different photos, and then a third negative sample that is a morph of person 3 and 4. So to describe the data sets that I use, the morphing data set, is I now have 434 what I call morphing identities, and we have about 30,000 photos, and we again save some for testing. Now we can look at the same results and compare what happens when you train the same face recognition system, the same architecture as before, but this time including morphs as separate identities. And then you see that you have the same effects. So during training, the network becomes better and better at separating the genuine and the imposter distributions. But the effect on the morphing accept rate, so the proportion of morphing comparisons that are accepted, is significantly lower. So if you remember before, it was around 0.14, here is at about 0.07, so it's almost halved. And when you look at the same data, but now plotted slightly differently, so here on one axis, you now see the false non-match rate at a fixed false match rate. So this is sort of roughly speaking a measure of how well the distributions are separated. And here, the lower, the better. The lower this value is, the better the distributions are separated. And the morphing accept rate describes that, shows that as you train a network that was trained without morphs, so only with normal photos, the separation of the distribution becomes better and better, but this is at the cost of the number of morphing comparisons that is accepted. And when you use the other training scenario where you treat morphs as separate identities, you still lower the false non-match rate at a fixed false match rate. So the separation of the distributions becomes better, but it is not at the cost of accepting more morph comparisons. So you do see here a caveat is that the separation of the distributions is not quite as good as it was when you train without morphs. So more experiments are needed. This is a first preliminary research. More experiments are needed to show whether this holds for different types of neural networks, different types of architectures, whether this holds for different kinds of data, and whether it is possible to lower the false non-match rate at a fixed false match rate further than we did here. So in a way that it is as good as a system trained with only normal photos, and whether this trend is consistent over different architectures and different kind of data sets. So far, we have had some results that seem to slightly contradict this. So definitely more research is needed. But these first experiments did seem hopeful, so we will continue working on this particular problem. Okay, thank you for listening.